A system has optionality when it retains the right, but not the obligation to take an action at a defined premium cost. The option is exercised only when the realized payoff exceeds the premium, otherwise it expires and the loss is limited to the premium. This creates an asymmetric payoff structure that is bounded below by zero. The floor is enforced by design. Optionality is a formal architectural property. It embeds a max operator into the system's response function. Holding an option is structurally different from holding a commitment. The option preserves the right to decide later. Optimization selects the action that maximizes a fully specified objective function over an admissible set. It commits to a single action before the uncertainty in the environment resolves. The argmax requires knowing the objective function IF in advance, its shape, its parameters, and its domain. Once the action is selected, the system is locked in. There is no mechanism to change the decision as information arrives. Optimization locks in a choice. Optionality defers the choice until more information is available. Optimization treats the objective as effectively linear in expectation. The argmax is determined by the objective function, not by the distribution of outcomes around the optimum. Optionality preserves nonlinearity through the max operator. The payoff is kinked and convex rather than smooth and linear. Committing to an optimized action removes the kinked structure and replaces it with a linear one. The commitment cost of optimization is the loss of the convex payoff structure that optionality provides. Under uncertainty, this commitment cost can be substantial when the realized outcome differs from the anticipated optimum. Standard optimization over the full admissible set may select actions that are optimal in expectation, but approach the absorbing failure boundary. Absorbing constraints restrict the feasible set to actions that exclude trajectories leading to irreversible failure. These constraints must be added explicitly to the optimization formulation. They are not present in the unconstrained argmax. Optionality naturally enforces an absorbing constraint through its floor structure. The system cannot be driven below zero by design. The difference in structural safety between optimization and optionality is therefore partly topological, not just numerical. By Jensen's inequality, the expected value of a convex function of x is at least as large as the function evaluated at the expected value of x. Applied to the option payoff, this means the expected option value exceeds the option value at the expected input. The gap between these two quantities is the Jensen gap. It represents the value that optionality adds relative to committing at the mean. This gap is driven entirely by the variance of x. Higher variance increases option value. The Jensen gap is the formal quantity that explains why optionality is more valuable in high uncertainty environments. Optimization is efficient when the objective function is fully known and the environment is stable. Commitment costs are low and the argmax is reliable. Optionality is valuable when the objective is uncertain or changing, and the premium cost of preserving flexibility is justified by the variance in outcomes. Optimization is fragile to objective misspecification. If F changes after commitment, the selected action may no longer be optimal. Optionality is robust to this failure mode because the decision is deferred until after information resolves. Neither strategy dominates universally. The choice depends on the structure of the environment and the cost of the option premium.